What we're going to discuss in this video is we're going to discuss something called parametric equations. Now up to this point, we're used to equations being a relationship between one variable and another, where we've got an independent variable and a dependent variable, i.e. one variable which as it varies, changes the other variable. So the independent variable changes, the dependent variable does something depending on what that does. Sometimes though, it may be worth it for us to represent both of these variables in terms of a third variable. So we may, for example, have an equation that represents a relationship between x and y, but introduce a third variable, let's call it t, which both of those x and y depend upon and can vary dependent upon that variable itself. This is what's called a parametric representation, and the x and y, which are both represented and dependent upon that third variable, again we'll stick with t, they're called parametric equations, and that t is what's called the parameter. What that means is every single new value of t will give a new distinct point on a curve which is given by x of t, y of t, where the positions x and y will change depending upon what we choose to be t. Now one thing that this may be useful to represent is your position with respect to time. So you may be able to use it to represent a journey where you represent how far along, how far up you go, i.e. your x and your y, but that may be dependent upon the time within the system. So your direction along, your direction up may change depending upon how long you have been travelling on that journey. So that's the style and the type of equation where it may be useful to use. Now what I may mean by this is if we take the example of the equation 3x plus 4y equals 24, so the straight line represented by that, which is given in this diagram here, we can represent that parametrically using x equals 4 bracket 1 plus t, y equals 3 bracket 1 minus t. So if I was to pick any value of t, I could substitute it into here and I'd get a distinct x and a distinct y such that I could represent this line using those values. So for example, we know here that y is equal to 6 as x is equal to 0. So if that was the case, if x was equal to 0, I'd have 4 bracket 1 plus t equals 0, and the y would be 6, so I'd have 3 bracket 1 minus t equals 6. If I was to work these out, what I'd end up getting for these is the same value of t, because at that point t, I'd be able to represent this coordinate using that. If I were to work out both of these little equations, what I'd end up getting for both is that t equals negative 1. So if I was to pick the parameter t within here and substitute it into this, I would get the coordinate 0, 6. If I were to choose 8, 0, so this coordinate here on my x-axis is the example, and set it into here, so I'd set 4 bracket 1 plus t equal to 8, and 3 bracket 1 minus t equal to 0, I could solve both of those equations, and again, I'd get a new value for t, but it would be the same for both. Because if I chose t to be equal to that number, that would represent the point given on the x-axis there. So we're able to use this to calculate our position for other points within our system. However, it is also possible for us to eliminate this parameter from the equation, and occasionally that can be useful because it gives us an idea of what we are representing within the system. So let's imagine I'm giving the x equals x of t and y equals y of t, so they're both dependent on this parameter t. If I was to take this first equation at the point t equals x to the minus 1 of x, i.e. the inverse of x, and substitute it into this equation here, we would get y equals y of the inverse of x. This is what's referred to as the constraint equation of the function, and it represents the overall system within which we lie. So if we go back to the previous example, what I was given was x equals 4 bracket 1 plus t, and I had y equals 3 bracket 1 minus t. If I was to multiply them out, I'd get 4 plus 4t, and for the y, I would end up getting 3 minus 3t. Now if I focused on x, what I would want to do is take this so that I get t equal to something by calculating the inverse. So if I was to do that, I'd have x equals 4 plus 4t. I could rearrange that, and what I'd end up getting is that t equals x minus 4 over 4. So that would be what t would be represented by in terms of x. If I then substituted that back into here, what I'd end up getting is that y equals 3 minus 3 times this x minus 4 over 4. If I were to then take this and simplify this whole equation, what I'd end up getting is 4y equals 12 minus 3x plus 12. I've just gotten rid of the denominator here by multiplying everything by 4 and then multiplying out the resultant bracket. If I were to then rearrange this, what I'd end up getting is 4y plus 3x minus 24 equals 0. And if we were to go back and look at the equation of that line as it was written previously, we'd actually find it's the exact same equation here. So what I've done is eliminated that parametric variable and got back to the original equation, which gives me the constraint equation of the function within that system. And it'll allow me to say this system represents a straight line. Now there's a couple of different scenarios that is actually really useful to represent parametrically, but one of the big ones is thinking of a circle. So thinking of parametric equations of a circle. Now let's start by considering a specific example where we say x is equal to 4 plus r cos theta and y is equal to 3 plus r sine theta. Now, where I'm getting this from is imagining I've got a system here where I've got a circle of a centre 4, 3 represented by this, and the r cos theta and the r sine theta represent my position on the circle where the distance from the centre to the circle itself is equal to r, and the angle here is theta. So the angle there between the horizontal and that line r is represented by theta. This direction along here is given by r cos theta, and the position going up and down the way is given by r sine theta. Yeah, we can split that off as if it's a little right-angled triangle, and we can use Pythagoras theorem as well as SOHCAHTOA to do some work and manipulate it. So it would be represented by this, r and r cos theta, and I've got r sine theta there like that, with my angle theta given here, and this bit here represents the point 4, 3 in my system. So this just enhances it and lets us look at it a bit more. Now for this we know r is a constant, i.e. it's the length of a radius, but we don't know the specific example yet. What I'm going to do is take this and eliminate what I'm going to call my parameter theta. Now we know that this is the parameter because as the angle changes, so will the positions x and y. So x and y are both dependent upon this theta, so theta is my parameter and these are my parametric equations representing it. So what I'm going to do is take the x one and I'm going to eliminate theta by getting it equal to each other. So if I take the x one, what I can say is that r cos theta equals x minus 4. Now I might be able to jig this about a bit and get cos minus 1 of something, but what I'm actually going to do is to look at the same sort of idea here and do r sine theta, and what that will give me is y minus 3. Now if I were to remember some of my trig identities, specifically cos theta plus sine squared theta equals 1, if I take both of these and square them and add them together and take out the r as a common factor, what I'll end up getting is that r squared cos squared theta, so that would be this one here squared, plus r squared sine squared theta that's going to equal the x part plus the y part. So that's going to equal my x minus 4 squared plus my y minus 3 squared. Now if I look at this side here, if I take r squared out as a common factor, I get r squared bracket cos squared theta plus sine squared theta. And as we've just stated here, cos squared plus sine squared is equal to 1. So I can rewrite this as x minus 4 squared plus y minus 3 squared equals r squared. And we know that that represents a circle, radius r, with a centre at 4, 3. So what we've done is we've said that we're able to manipulate these here, the parametric equations of x and y, and turn them into a constraint equation, which represents that circle, which we've just described. So this here would be our constraint equation. These two here, so the parametric representations of x and y, for this scenario, they have a special name which is called the freedom equation. So these are the freedom equations for this system. And they're represented in terms of cos and sine with relation to r, the radius of our circle. So this is where the idea of that being the equation of a circle comes into play. So if we remember, we had x minus a squared plus y minus b all squared equals r squared being our generic equation for the equation of a circle of centre AB and radius r. This is where it comes from. This is the fundamental idea behind it. So let's imagine I've got two examples here. So I'm going to say to you to find the constraint equation of the locus defined by the parameters x equals t plus 1 over t and y equals t minus 1 over t, and find dy by dx. Now, what we could do to eliminate the t and find the constraint equation is rewrite it so that we have t equals something in terms of x, and then substitute it in. However, the manipulation for this requires a lot of work in this side of the equation. So what we're going to do is we're going to take these equations and we're going to square both of them, and then from that we're going to then subtract them from each other. So if I were to do the x, I'd have x squared equals t plus 1 over t all squared, and if I were to multiply this bracket out and simplify it, I'd have t squared plus 2 plus t to the minus 2. We're going to be working with derivatives, so let's keep them as powers. If I were to also do the same with the y, I'd get y squared equals t minus 1 over t squared. And if I were to then multiply out the brackets and simplify that one, I'd get t squared minus 2 plus t to the negative 2 for y. What I'm then going to do is to eliminate all of the t's, and notice that if I subtract the x squared and the y squared, I'll get rid of everything and I'll just be left with a constant. So if I do x squared minus y squared, what I'll end up being left with is just 4. So I've eliminated the t's from there. I've got something left just in terms of x and y, and that's my constraint equation there. Now it almost looks like a circle. However, this one here, because it's a minus, this isn't the equation of a circle. So we have to bear that in mind when we're working with it. The second thing it wants me to do is find dy by dx. So what we do is we treat this as implicit differentiation. So we go along, differentiate every term on its own, and rearrange it. So if I were to do that, what I'd end up getting is 2x, take away 2y dy by dx, equals 0. And if I then rearrange this, what I'd end up getting for this one is that dy by dx equals x over y. So there you go, I've calculated dy by dx in terms of x and y for that equation there. Now we could be asked to do a bit more with this sort of equation. We could be asked to sketch it, manipulate it, talk about limitations that are on it. But in this case, what I wanted to do in this example is just show you how we could eliminate it and how we can calculate derivative. Remember, the key thing is that we want to eliminate the t. Whether that's just direct substitution, which we could have done, it would just have required a lot of manipulation, or a technique along these lines, get rid of it. That's the key aim and that's the key goal in this one.